SwayamPrabha. Digital India. Educated India.
Good morning. This is the third lecture on axial flow steam turbine. Contents of the lecture are axial flow steam turbine, impulse turbine, blade efficiency or the diagram efficiency, stage efficiency, optimum blade speed and efficiency. I have discussed here about impulse turbine. Impulse turbine is an assembly of nozzle and rotating blades. The pressure remains constant as the fluid passes through the rotating blade. I have indicated C as absolute velocity, W is the relative velocity, U means the blade speed, alpha indicates the absolute angle with respect to tangential direction, beta means the relative angle with respect to tangential direction, 1 indicates inject to the blade, 2 means exit from the blade, Z is the axial direction and theta be the tangential or peripheral direction. Regarding sign convention of the turbine, I have considered clockwise direction is positive. Thus, I have presented here the nozzle along with the rotating blade. The nozzle is down with respect to by the reading, while the rotating blade is presented by the bluing. Please note that C1 with the velocity of fluid at the exit from the nozzle that makes an angle alpha 1 with respect to tangential direction. With respect to the rotating blades, W1 be the relative inlet velocity and W2 be the relative exit velocity. That makes an angle beta 1 and beta 2 respectively. Z indicates the axial direction and theta be the peripheral direction. U is the blade speed as I have told earlier. Now I have drawn the velocity triangle at inlet and exit. So vectorial addition of W and U will give C. So W1 plus U1 is equal to C1. W1 makes an angle beta 1 and C1 makes an angle alpha 1 with respect to tangential direction. Similarly, at exit W2 plus U is equal to C2. W2 makes an angle beta 2 and C2 makes an angle alpha 2 with tangential directions. This is so far regarding the assembly of nozzle and rotating blade. That's a simple impulse turbine. I have presented here combination of inlet and exit velocity triangle. Inlet velocity triangle is presented here by the blue ink, while the exit velocity triangle by red ink. Now please note that W1 plus U is equal to C1 and W2 plus U is equal to C2. Corresponding angles such as beta 1 and beta 2 is presented here, and so alpha 1 and alpha 2. Note that the projection of C1 is indicated by C theta 1, swirling component of C1. Similarly, swirling component of C2, that is projection of C2 on the tangential direction, is represented by C theta 2. Here C theta 1 plus C theta 2 will give del C theta, and CZ1 be the axial component of C1. Similarly, CZ2 be the axial component of C2. Now this is so far the combined velocity triangle. Now let's come to the discussion of impulse turbine. I have already told that pressure within the rotor remains constant for an impulse turbine, and if we neglect the friction, that is for ideal case, since the pressure remains constant, W2 must be equal to W1. But in reality, when there will be friction, W2 would be equal to less than W1. However, for a reaction turbine, W2 would be greater than W1 as the flow accelerates within the rotor. Now let us consider the actual case, that is impulse turbine with friction. Then W2 I have represented as K into W1, where K is treated as frictional coefficient, or it is also referred as the blade velocity coefficient. Thus, K is equal to W2 by W1, where K is less than 1 considering the friction. If we neglect friction, then W2 would be equal to W1. Now, considering the velocity triangle, the tangential force on the blade is expressed as F is equal to M into C theta 1 minus T theta 2, that is equal to M into del C theta, where M is the mass flow rate through the turbine and del C theta is the change in swirling component, and considering sign convention, C theta 1 is in the direction of U and it can be treated as positive, while C theta 2 being in opposite direction of blade speed, it can be treated as negative. Thus, F can be expressed as M into C theta 1 plus C theta 2 in this direction, considering the velocity triangle. So this is the expression of tangential force, which is M into C theta 1 plus C theta 2. Now, axial force or thrust for which a bearing would be designed is equal to M into CZ1 minus CZ2. Now, since W1 and W2 they are unequal, there would be some thrust on the turbine, and this expression of thrust would be M into CZ1 minus CZ2. Now, work output W can be expressed as tangential force into blade speed. So W is equal to M into del C theta into U, where del C theta is equal to C theta 1 plus C theta 2 and U being the blade speed. After evaluation of work output, I can define the blade efficiency and the stage efficiency. The blade efficiency or diagram efficiency is defined as work output divided by kinetic energy of jet. Thus, eta B is equal to m into del c theta into u divided by half in c1 square. C1 be the velocity of jet coming out from the nozzle. That is, eta B equal to twice del c theta u divided by c1 square. Now the stage efficiency eta S would be defined as the ratio of work output per unit mass flow to the total isentropic enthalpy drop. That is, it can be stated as eta S equal to del c theta into u divided by del H isentropic, where del H isentropic represents the isentropic enthalpy drop in the assembly of nozzle and rotor. Therefore, eta S can be expressed as twice del c theta u divided by c1 square into c1 squared by 2 divided by del H isentropic. Hence, stage efficiency is the multiplication of blade efficiency and nozzle efficiency. I'm going to present an important section where I'll derive the blade speed for which the blade efficiency would be maximum. I have presented here optimum blade speed of a simple impulse turbine for maximum efficiency. So I have considered the superimposed velocity triangle of a simple impulse turbine. Hence, from the velocity triangle, del c theta is equal to w theta 1 plus w theta 2. That is, del c theta is equal to w1 cos beta 1 plus w2 into cos beta 2, which can be indicated as w1 cos beta 1 within the bracket 1 plus w2 by w1 into cos beta 2 by cos beta 1. For a symmetric blade, beta 1 would be equal to beta 2. For asymmetric blade, beta 2 and beta 1, they are not equal. So I can consider cos beta 2 by cos beta 1. The ratio is some constant which is represented here by C. Furthermore, I know W2 by W1 is equal to K, which is frictional coefficient. Thus, del C theta is equal to W1 cos beta 1 within bracket 1 plus K into C. Now, W theta 1 can be equated with C theta 1 minus U. Just I can write W1 cos beta 1 is equal to C1 cos alpha 1 minus U within the bracket 1 plus K into C. So this is the expression of del C theta with respect to C1 cos alpha 1 U and K and C. Now we have indicated earlier that blade efficiency is equal to twice del C theta U divided by C1 square. Thus from here put the value of del C theta here. Thus eta B blade efficiency is equal to twice U divided by C1 square within the bracket C1 cos alpha 1 minus U within the bracket 1 plus K into C. So this is the expression of eta B, blade efficiency. Let us consider now the speed ratio as rho is equal to U by C1, where U is the blade speed and C1 is the velocity of jet coming from the nozzle. Thus, eta B can be expressed in terms of rho as twice rho within bracket cos alpha 1 minus rho within the bracket 1 plus Kc. Now I have rearranged here, that is eta B is equal to twice within the bracket 1 plus Kc, again within the bracket rho within the bracket cos alpha 1 minus rho. Now let me pause over here. For a certain design of impulse turbine, the K, which is the frictional velocity, can be treated constant, frictional coefficient, and C, which is the ratio of cos beta 2 by cos beta 1, can also be treated as constant. Therefore, the eta B is a function of rho only, because here alpha 1 can be treated also constant. Again, let me explain. For a certain design, K, C, alpha 1 may be treated as constant. Thus, eta B is the function of rho only. Thus, for maximum efficiency, I can say d eta B by d rho is equal to 0. Thus, from here, I can get rho is equal to cos alpha 1 by 2. That is equal to U by C1. Put the value of rho, that is cos alpha 1 by 2, in the expression of eta B, then you will get maximum value of eta B. Thus, eta B max would be cos square alpha 1 into 1 plus Kc divided by 2. This is the maximum expression for maximum eta B for a simple impulse turbine. Now, if we consider the blade are symmetrical, then beta 1 should be equal to beta 2, and thus C must be equal to 1. Further, if we neglect the friction, then K is equal to 1. Hence, under this constant, that is, for symmetrical blade with no friction, eta B max, that maximum efficiency of an impulse turbine, would be equal to cos square alpha 1. Now, let us consider a special case of a Pelton wheel. For a Pelton wheel, we know that alpha is equal to 0, and Pelton wheel is an impulse turbine. Thus, when alpha is equal to 0, rho would be equal to half. That is, U by C1 is equal to half. This is the condition for maximum efficiency of a Pelton wheel, and hence U would be equal to half of C1. So from here it can be concluded that if the blade speed of a Pelton wheel be the half of jet speed, then the efficiency would be maximum. Now let me come back to the simple impulse turbine, that's a steam turbine. Now I have already proved eta B max is equal to cos square alpha 1. So thus it should be noted that as alpha 1 decreases, eta B max increases. Further, with a decrease of alpha 1, the mass flow rate and hence the power output decreases. Hence, the value of alpha 1 is recommended in between 15 to 25 degree. I like to indicate here that exhaust from the stage, that is C2, is associated with kinetic energy loss. This kinetic energy loss would be minimum when C2 would be axial. Thus, it can be proved that for optimum blade speed or optimum efficiency, the exhaust from the stage C2 would be axial. Now I'll discuss about velocity compounding. If the blades used are symmetrical, that is beta 1 is equal to beta 2 with no friction where k is equal to 1, and the exhaust velocity from the stage C2 be axial, then it can be proved for velocity compounding that rho optimum would be equal to cos alpha 1 divided by 2n, where n is the number of rows of moving blade. I have already indicated that velocity compounding is done to decrease the blade speed. Here I have already indicated that optimum blade speed is lower by a factor n, where n being the number of rows of moving blade here. Furthermore, since the second row of blade generates a fraction of work output of the first row, then eta b decreases with n. Further, n beyond 2 is not recommended. So here I have indicated the performance of velocity compounded turbine, where x-axis indicates the blade speed ratio, that is U by C1, and the y-axis indicates the blade efficiency. Now I have superimposed here the blade efficiency when n is equal to 1, and 1 means is a simple impulse turbine, n equal to 2 and n equal to 3. What has been observed that with increase of n, the optimum blade speed decreases, whereas the efficiency also decreases. Thus, for n is equal to 1, which is a simple impulse turbine, rho optimum would be equal to cos alpha 1 by 2, and efficiency is cos square alpha 1. For n is equal to 2, the optimum blade speed ratio would be equal to cos alpha 1 by 4, and the efficiency is decreased. For n is equal to 3, optimum blade speed ratio is cos alpha 1 by 6, and efficiency is further decreased. So this is the performance of velocity compounded turbine. What are the advantages of a velocity compounded turbine? Here it accommodates a high enthalpy drop per stage. Furthermore, the blade speed decreases with respect to n. As n increases, blade speed would decrease. Here I have discussed about an impulse turbine. I have also derived the expression for optimum blade speed ratio and the maximum possible efficiency of an impulse stage. Furthermore, I have discussed about velocity compounded turbine. Thank you for listening.